In our example case, people used to collect fuel wood on the project area. Remember that this was 800 hectares. To determine the leakage, we now have to find out how much of these activities will eventually shift to other places outside the project area. The results of a survey in the surrounding villages shows that 90% of the people collected their wood in the area which will become our conservation area. As we will not plant any trees here, we allow people to continue to collect their wood on this area. The remaining 10% of people will change their habits and move to other land outside the project area to collect their wood. For the conservative approach, we take the worst case scenario. Considering that these 10% will unsustainably collect their wood outside the project area, we have to consider that they will eventually deplete a forest in the neighborhood of the project. According to literature, forests surrounding the project have a mean above-ground wood stock of 150 cubic meters per hectare, which converts to 200 tons of CO2 per hectare. Multiplying now the area times the potential emissions which will be caused by the shift of activities, we derive a total leakage effect of 10,000 tons of CO2 for our category A, fuel wood use. Note that within our calculation of fuel wood use, we did not consider the collection of fuel wood from dead biomass, as this is not a preset carbon pool. In our example case, we have another activity shift, which falls under some kind of mixture of leakage types, as it is a shift of a farmer together with its farming land. Although this farmer was owning the entire project area, he was only planting maize on 10 hectares within the project area. With the money of the sale of his land, the farmer bought himself a nice house in the city nearby. Therefore, although 100% of the people had to change their habits, no significant CO2 emissions can be expected. Therefore, no leakage effect is given from this kind of activity shift. In contrast to the previous leakage types, which both fell under the category of human, we will now calculate an example which is of the category livestock. You will see that hereby different parameters must be used for its calculation. The farmer, which has sold his land, did not do agricultural farming, but was also leasing his grass and shrubland to his neighbor who had put 300 cattle on it. As we will now plant on this area, this livestock will have to be shifted. According to the neighbor, he only wants to keep 50% of the herd, so 150 cattle. For these animals, he now buys other land somewhere close by, which is similar to the shrubland on our project area and therefore contains, on average, 20 tons of CO2 per hectare. According to literature, 2 hectares per cattle are necessary for sustainable livestock management. So, using all of these parameters, we derive a leakage effect from the shift of livestock of 6,000 tons of CO2. And whoever was wondering what happens to the remaining cows? Summarizing now all the leakages, we conclude with a total leakage of 16,000 tons of CO2. This time, we have to divide this sum by the total project area of 800 hectares, which gives us a leakage effect of 20 tons of CO2 per hectare. Now, as we have determined all necessary parameters, we are able to calculate the net CO2 fixation of our management unit number 1. Therefore, we take the 490 tons of CO2, which will be stored in our forest, minus 3 tons of project emissions, minus 14 tons of CO2 resulting from the baseline, and minus 20 tons of leakage, which gives us 453 tons of net CO2 fixation per hectare. Multiplied by the eligible area of the management unit, which is 100 hectares, we derive a total CO2 reduction of 4,530 tons of CO2. This also represents the amount of VERfutures which will be issued with a successful certification. After having calculated the different values, we are now going to see how you fill this into the templates that are available within your login area. To learn in detail how to register a project and how to work with other templates, please watch the web tutorial How to Register Your Project. The templates Future CO2 Fixation, Baseline, and Leakage are available in your account under the menu link Templates and Guidelines. There, you can download them from the red table CO2 Fixation. After having downloaded these documents to our computer, we will now look at how to work with them. We start with the template Future CO2 Fixation. As it is the case in all templates, the respective criteria of the CarbonFix Standard are copied. If we scroll down, we get to a section where you can fill in up to 8 different growth models. In the growth model table, you have to show how you got your figure of sequestrated CO2. This is the result of the formula on top. In the table, we fill in the variables we used in this calculation and how we got to these formulas. You start by giving the particular growth model an ID, for example, mixed 1. Then you have to choose your option of calculation. As you might remember, you can choose between selective harvesting, rotation harvesting, or conservation forests. We continue working with our previous example, which means that we use selective harvesting. Then we enter for how many years our growth model was tested. In our example case, the growth model was tested for 60 years and predicts that the forest reaches its equilibrium in year 40. Next, you select the type of calculation you used. As we already learned, here you can choose between the equilibrium stand volume, the maximum stand volume in the first 50 years, the mean stand volume, or the mean stand volume in the first 50 years. As we worked with selective harvesting and our forest reached its equilibrium before year 50, we chose equilibrium stand volume. Next, you will select how many cubic meters per hectare the growth model predicts when a forest reaches its equilibrium. As we saw before, our forest will have 324 cubic meters per hectare. Then, in the next box, you will select how many inventories have already been executed. This enables the certifier to control the accuracy of your growth model. In the next box, you have to enter the factors you are using to calculate the meters cubed as predicted by the growth model and the inventory to the amount of sequestrated CO2. How this is done we have seen before in the chapter conversion procedure of this web tutorial. So, the biomass expansion factor, the wood density, and the root-to-shoot ratio we found in the literature. You should always try to find local values for these parameters. In case you can't find a local value for one of these variables, you may use a national value. When that is also not available, you may use an international value. If even that is not available, CarbonFix provides default values for each of the parameters which can be found within the CarbonFix Standard. These must only be used when the others are not available. In the row below, we have to put in the literature references of the values we use. The source from which you got this information should always be attached to the template as a zip file. At the final box of this table, we then fill in the results of the calculations with our variables. With the first formula, we calculate our above ground biomass. This is our stem volume of 324 cubic meters per hectare times our biomass expansion factor of 1.3 times our wood density of 0.5 times our carbon fraction of 0.5 times our carbon to CO2 factor of 3.6666, which gives us a woody above ground biomass of 386 tons of CO2 per hectare. Our below ground biomass is our above ground woody biomass times our root to shoot ratio of 0.27, which gives us 104. This gives us a total tons of CO2 per hectare of 490, which you fill in the cell at the bottom of the table. Under it, we can read that the result must be transferred into the web system of the project. We will see how this works after we have explained the remaining templates. When we have filled in everything, we print this template in PDF, so we can later upload it onto our account. When you print it, only print the pages that you have filled in. In our case, the pages 1 to 3, as we only use one growth model. So, let's go together to the next template, baseline. We have already seen how we calculate the baseline and which carbon pools need to be included. Again, the templates show first the criteria of the CarbonFix Standard from this particular chapter. Then below, there are 2 types of tables available. 4 tables for the calculation of wood baselines and 3 tables for the different non-wood baselines. As we have seen before, the baseline is only determined for the eligible area of the project. The result of the formula on baseline calculation was in our example case 10 tons of CO2 grassland baseline and 20 tons of CO2 shrubland baseline. In contrast to the CO2 fixation, the name of these tables is preset to 1, 2, 3, and 4. In the template, we have to justify how we came to our shrubland baseline. Again, we have to enter the stem volume we found and, when necessary, the form factor we used. Then we continue with the biomass expansion factor and the wood density. Carbon fraction and the carbon to CO2 factor are again default, and we can eventually enter our root to shoot ratio. Again, under this we have to write down the reference of our information and whether the parameter was a local, national or international value, or even if the CarbonFix Standard default value was used. Also, here the sources have to be uploaded with the template as a zip file. These parameters we will fill in the formula on top, and the result we put down in the cell at the bottom, which in our case was explained earlier, 20 tons of CO2 per hectare. Then, to the right, we fill in the total area that is covered by this particular baseline. Also, we select which area this refers to. In our case, it was others. It is only part of the eligible planting area. At the bottom of this column, we fill in the total baseline emissions for this type, which is the baseline per hectare for the column at the left, times the part of the eligible area covered by this baseline. The same way we can enter the grass baseline we found. Therefore, we scroll down to the table for non-wood emissions. The filling in of this table works basically the same, only here other factors are used as it calculates non-wood baseline. The formula to convert from tons of fresh biomass to CO2 per hectare is shortly stated above. Also here we have to fill in the factors we used and refer to the source of these values. As we remember, the result of the calculation in our example was 10 tons of CO2 per hectare, for a total area of 300 hectares. Which gives a result of 3,000 tons of non-woody baseline CO2.